Hello, everyone. My name is Fuheng Zhao. I'm from University of California, Santa Barbara. Today, I'm presenting our work, Pentacles, Chasing the Tails for Multidimensional Data Streams. This work is done in collaboration with Pano, Divi, ARM, Arpe, and Allen. In the sensor and network system context, often we can split the whole system into data plane and control plane. Data plane is responsible for processing all the data, and control plane decides how data should be processed. Periodically, hardware in data plane will send traffic information to the control plane. Based on the collected statistic, the control plane will update the processing protocol in the data plane. Often, system operators and administrators want to learn key insights from the data traffic, such as feature distribution and tail contributors, for implementing better protocol or detecting anomalies. As an example of data plane, software-defined network uses network switch to collect statistics about network packet streams. Network switch have multiple data processing stages, and each stage has limited computation power and local storage capacity. Usually, there are 2 to 10 stages and hundreds of kilobytes of memory. Also, data can only process from left to right. It is a one-way direction. In Pentacles, we aim to solve the following problems and challenges. First, we want to approximate the feature distribution accurately. Feature distribution is also known as frequency distribution, flow size distribution, or degree sequence. Note, distribution may dynamically changes, and we assume feature space is predefined by the user. Second, we want to identify tail contributors. Given a feature distribution shown as at the right, we want to identify all features associated with high quantile values, essentially the tail of the distribution. Moreover, our proposed pipeline should be able to fit in the hardware with limited memory and compute. To illustrate feature distribution, here's an example. Assume feature arrives sequentially. First A, second B, and then C. At this time, there are 3 features, each with a matrix value of 1. So as a result, if we view it as a histogram, matrix of 1 has a count of 3. Next, assume 2 A's and B arrives. At this point, feature A has a matrix of 3, feature B has a matrix of 2. If we look at the feature distribution, which is represented by the cumulative distribution function, it looks like a straight line. In real world, often the stream follows Zipf laws. To represent feature distribution in database context, we can rewrite them in terms of SQL, where feature distribution is essentially the cumulative distribution over the matrix. Here we assume we're using the count operators as the matrix, and then we calculate the feature and the cumulative distribution over the matrix. In addition, the tail contributor can be seen as select features as tail contributors from feature distribution where quantile value is above the threshold. In this example, we assume the threshold is 0.99. There are many prior works solving one of the problems, but not all of the challenges and problems. For instance, MRAC uses an array of counters and 1 hash functions to approximate feature distributions. However, it does not track feature identity. As a result, it cannot be used to approximate tau contributors accurately. Augmented sketch uses 2 stages to track features. However, its implementation requires communication between these 2 stages and cannot be efficiently implemented in hardware. Elastic Sketch also uses 2 stages. The first stage stores half features in a hash table, and then the second stage stores evicted features in an 8-bit counter array. When memory size is small, warm features can cause overflow in the counter array, and as a result, it cannot be used to approximate feature distribution well. FCEM built a hierarchical tree structure over multiple common. However, the collision probability among half features grow exponentially as the tree depths. As a result, we introduce our solution, Pentacles. Pentacles consists of 3 stages. The first stage is BMAP stage. Assume you have a stream of features. The first feature is E5, and we have a hash function to map the feature into a bucket. Each bucket has a counter, and we increment the counter by 1. When the counter overflows, the feature is moved to the next stage. The BMAP stage is used to capture co-features and derive stream cardinality. In the common stage, it is used to capture warm features. In addition, unlike the BMAP stage, we use multiple hash functions. By using multiple hash functions, we reduce the collision probability between features exponentially with the number of arrays. Similarly, each hash function will map to a bucket, and we increment the counter of that bucket by 1. If at least one of the counters overflows, then the feature is moved to the last stage. In the last stage, we use space saving. Infrequent features are filtered out, and we store feature identity explicitly to improve accuracy in identifying tau contributors. Here, we want to talk about some intuitions for why Pentacles is highly accurate for the above-mentioned 2 problems and the challenge. The BMAP stage uses 2 bit counters to maximize the length of the array in stage 1 and achieve highly accurate estimations on cardinality, number of singletons, and number of doubletons. In the common stage, we use multiple arrays to avoid hash collisions between warm and hot features. And lastly, the space saving stage proves optimal space accuracy trade-off for insertion-only and bounded deletion stream. For more information, refer to the mathematical analysis section in the paper. In experiments, we compare we showcase approximate feature distribution and identifying tau contributors. In feature distribution, we use quantile arrow to measure the difference in terms of y-axis, as shown in the figure on the right-hand side. In addition, we also measure the matrix arrow, which is the arrow in terms of x-axis. We use the standard F1 score to measure the tau contributors. F1 score is the harmonic mean of precision and recall. For this presentation, we showcase experimental results over KDA dataset. KDA dataset contains anonymous network packet trace between Seattle and Chicago. We assume the feature space is source IP, destination IP, source port, destination port, and protocol. And the stream length used is 1,000,000 packets. For feature distribution, the x-axis is the space, range from 8 kilobytes to 128 kilobytes. And the y-axis is either maximum quantile error or the average relative error. Here, the blue line is Pentecost, and lower y-axis value means better accuracy. We can see that Pentecost in general achieves the best accuracy in both matrix and quantile for approximating the feature distribution. In the matrix domain, Pentecost is clearly the winner. In quantile domain, when stream is extremely tight, Elastic achieves better accuracy by store features in hash table. However, it does not scale well. For tail contributors, the axis is also space, range from 8 kilobytes to 128 kilobytes. And the y-axis is F1 score. Higher F1 scores means better accuracy. We assume the quantile threshold is 0.99. No solution achieves good F1 score when memory is extremely limited. And we can see that Pentecost achieve high F1 score in identifying tail contributors when the space is about 32 kilobytes to 128 kilobytes. In conclusion, we considered how to efficiently approximate the feature distribution and coin the problem of tail contributors by proposing our solution Pentecost. Please check out our paper for more details of the algorithm. In addition, we'll consider not only the count operator, but also sum and average operations. There are more experimental results on other real-world datasets, and including experiments over cardinality and entropy estimation. Moreover, we implemented Pentecost in software and hardware, such as P4 switch. Thank you.